FaultSpark is a fault-defining dynamo. It empowers your interpretation by automating the fault extraction process, replacing ceaseless mind-numbing mouse clicks with seriously speedy workflows and highly precise results. This valuable solution allows you to identify and construct fault planes quickly and accurately illuminate the overall architecture of the fault system. We will now overview the FaultSpark workflow. Our starting volume, shown here, has significant noise. Our goal is to use FaultSpark to remove that noise. The example dataset we are viewing here is Grand Isle West Delta, offshore Louisiana in the Gulf of Mexico. The seismic survey has north to south striping throughout the dataset. This striping is acquisition footprint. In a vertical section, the acquisition footprint can be seen going vertically through the entire dataset. The speckling noticed in the shallow and deep areas of the dataset is random noise, as shown here. Both acquisition footprint and random noise are visible as discontinuities in the seismic reflections. Our eventual goal is to use the real discontinuities in the seismic reflections to image the faults. When acquisition footprint and random noise are removed, faults can be cleanly and accurately imaged by discontinuities in the seismic reflections. Here are the results of applying Insight Earth's footprint and random noise removal processes. The north-south acquisition footprint striping has been removed. Here we can see in a vertical section of the original data how bad the acquisition footprint in random noise looked prior to applying Insight Earth's noise removal. Here is the noise removed volume. The speckling or random noise has been removed by using a dip-oriented, edge-preserving random noise removal filter. All of the detailed information needed for fault interpretation and stratigraphy is retained. In Step 2, we will use the noise remove volume to create an edge stack volume, Insight Earth's coherency attribute volume. Now let's go to an Insight Earth live interpretation and create the horizon edge stack attribute volume. Here we see the horizon edge stack volume. Insight Earth's dip compensated edge calculation images faults as black zones in the dataset. On a horizontal slice, faults are clearly imaged by the continuous black features. The other small detail between the faults are depositional systems, or stratigraphy. Here we see the horizon edge stack volume co-rendered with the seismic volume. Faults are clearly aligned to the seismic data and imaged by discontinuities in the dataset. Although faults are imaged well on horizontal slices, they are not imaged well enough on vertical slices to automatically extract fault surfaces. In the next step, we'll use the horizon edge stack volume as input to advance fault imaging. Let's again go to Insight Earth for a live interpretation. The horizon edge stack volume is used as input to advanced fault imaging. Advanced fault imaging produces several attribute volumes, including a fault probability volume, as shown here. The faults are now imaged crisply enough to automatically track in 3D and automatically extract fault surfaces. In this view, the polarity has been flipped to compare results. Here we see a horizontal slice view of the edge stacked input volume. The fault probability volume is shown here. The advanced fault imaging process filters out the weaker signal associated with depositional systems and improves the imaging of the faults in the dataset. Other attribute volumes created during the advanced fault imaging include the fault azimuth and fault dip volumes. The fault azimuth volume is shown here. Fault azimuth values are imaged where we have fault probability higher than a set threshold level. The rest of the volume is transparent. Colors indicate the different azimuth the fault has along the fault surface. The fault dip volume is shown here. Fault dip values are imaged where we have fault probability higher than a set threshold level. The rest of the volume is transparent. Colors indicate the different dipping angles along the fault surface. In step 4, fault interpretation, we will create the fault surfaces from the fault-enhanced volume. Let's again go to Inside Earth for a live interpretation demonstration of creating the fault surfaces. Inside Earth provides several approaches to interpret faults in this volume. One approach is to auto-track the fault in 3D. We do this by placing a single seed point on a fault to start the auto-tracking. Other seed points may be added to quickly interpret the 3D fault. Another approach to interpret faults is to extract fault cuts. The fault probability and fault azimuth volumes from the prior step are used to extract fault cuts and then create the fault surfaces. Here are the 3D fault surfaces. The fault extraction process accurately images intersecting surfaces. Here we see two faults very similar in shape that do not connect in the seismic data. The fault cut extraction process properly separates the two fault surfaces. Usually this is a difficult interpretation problem to solve. In conclusion, FaultSpark is a fault-defining dynamo. It empowers your interpretation by automating the fault extraction process, replacing ceaseless mind-numbing mouse clicks with seriously speedy workflows and high precise results. This valuable solution allows you to identify and construct fault planes quickly and accurately illuminate the overall architecture of the fault system. You can also utilize the fault surfaces generated during the process to provide further insight into the true stratigraphic environment. With FaultSpark, you get cleaner planes, trustworthy interpretation, and superior fault definition in the first pass. In fact, no other system even comes close.